good afternoon, and since it is in the afternoon, I want to see if I can wake the audience up a little bit by saying that I hope that this turns out to be an interactive presentation, if not during the presentation itself, actually afterwards. And the reason why I say this is because I have not attended a conference like this before to address this type of topic. Generally, the carbon nanotube community tends to be somewhat, for want of a better term, incestuous. And the people tend to interact with each other and don't go outside to listen to alternate views of things. And that can be dangerous in science and engineering when you don't solicit outside opinions. And I think that in this case, not doing that, not looking at this evidence the way I'm going to present it, I'm not saying I'm right, but I will be open to discussion, questions, shall we say, protective of their materials. And no one likes to be told that their baby is ugly. But right now, I'll say this, that unless we do make some changes, I often say carbon nanotubes are the materials of the future, and at this rate, they always will be. So let's start talking off. The speaker before gave a very nice, much more eloquent way of expressing this. There will be a little bit of math, but the question is, should we use quantum or classical approaches? And according to this Russian gentleman, Dr. Parman, we're safe to assume that we can use classical thermodynamics for the types of scales and materials that we're involved with here. So for those of you who haven't heard about carbon nanotubes, and I'm sure there's some people up in the Yukon that haven't, but most people in chemistry and engineering have heard of them. They come in three flavors. The first is the single wall nanotube, which basically is just that, a rolled up piece of chicken wire, for want of a better analogy. It comes in two forms, metallic and semiconducting, and that's based on the amount of axial twist around the center axis. Dual wall nanotubes are also present, but they're generally not a desired product. They generally occur as secondary products in most processes. Multi-walls are the easiest to make. They can be made by the metric ton, and they just are the ones, if you generally buy nanotubes and you want to get nanotubes at a reasonable price, they're the ones that you're going to get. They have graphitic layer spacing between the walls, so you're talking about something that's very easy to count the geometry and figure out where everything is. Now, how do you make carbon nanotubes, at least on an industrial scale? And generally, you use something like this. It's very simple. You have hydrogen. You generally need a reducing environment for this. You have, and I'll use this term with a little bit of, well, for want of a better term, catalyst precursor. There has to be a carbon source. Carbon sources can be anything. I have made nanotubes out of everything from mobile high-test gas to pesticides to vodka. Any carbon source will really make nanotubes. In this case, the popular one these days turns out to be methane. A sulfur source, you need an adjuvant, usually elemental sulfur, although some thiol compounds will also do. I'll explain that later. And generally a diluent gas, typically argon, because it's cheap and non-reactive. And this reaction, just to give you an idea, there's a gradient there that suggests a temperature gradient. The reaction temperatures are typically between maybe 800 degrees C up to about 1300. Those are generally where the furnaces tend to give out, burn out, and you're left with nothing. So here's our accepted growth model, and I say accepted parenthetically, but iron precursor decomposes into iron atoms that then assemble as iron nanoparticles. The carbon source gas encounters that nanoparticle, absorbs on its surface, and then again catalytically decomposes into carbon atoms and byproducts. Byproducts absorbed, carried away the gas stream, the carbon remains, and lifts off after it forms a cap. And the process should continue for as long as carbon is being supplied. Well, there's a couple of things that are troublesome to me about that. First of all, at these temperatures, they've always noticed that the particle is a liquid. And so if you have a liquid, generally catalytic processes, and I'm sure everyone in this room are aware, require a substrate, some sort of intermediate. They generally don't have things dissolving into the substrate as free atoms and sort of roaming around. I'm not saying that it's impossible, but I'm saying it's more of a solution-solute type of relationship. And for that, we can thank Adolf Seyfertz, who 100 years ago studied all this. For those of you who know what Seyfert's law is, it says that simple polyatomic simple molecular gas, is fairly disassociated to atoms when they encounter a metal, liquid metal. This, by the way, is also one of the most widely misquoted articles that I've ever come across in my career. No one ever bothers to read it, the original German. I can, so I did. But if you take a look at most textbooks, you'll notice that this thing is constantly referenced, but no one ever actually reads it. The one thing that Sieverts did point out, this is extremely interesting from a scientific point of view, is there is a special case for carbon, because carbon is the only atom in most common organic molecules that does not form a diatomic gas. It stays there. Nitrogen can form N2 and get the heck out. Oxygen can form O2 and get the heck out. Hydrogen can do the same thing. Carbon, once it dissolves as an atom in a liquid, it's stuck. So let's take a look at this again from a slightly different perspective, and that is that you have some sort of feedstock molecule that encounters a liquid. It dissolves as free atoms, as they will at these temperatures. Some of those free atoms can exist in equilibrium as free diatomic molecules. And so the hydrogen goes away, the nitrogen or any of the other gases that would be generated from the decomposition of the feedstock go away, but the carbon remains. Now here's something that's interesting. This is something that we've noted many times, and that CNTs have a particular relationship in terms of their diameter to the diameter of the catalyst particle that grows them. This is grossly cleaned up and very Euclidean. But the one thing that is observed, and this is something that I always found interesting, is this number right here. And this has been observed experimentally. Some people in the room will recognize that number. It occurs a lot in nature. It has a particular meaning. Why this happens here, I have no idea, but it has been observed many, many, many times. The important thing here is that it establishes the relationship between the particle and the tube. And so you typically need a tube that's slightly bigger, or a particle that's slightly bigger. To grow a 1 nanometer diameter tube, you need a nanoparticle that's 1.6, and so on. So this is nice because if you have a nanoparticle of iron, well, in bulk, carbon has a terrible solubility, iron. But in a nanoparticle, there is a difference in the cohesive energy density on the surface and then in the liquid layer further down. And you want to, you go to Joel Hildebrand. He came up with the Hildebrand solubility parameter. Very interesting little relationship that describes this and explains it. He was much smarter than I am, so I'm not going to try to butcher it here. So you can grow tubes. You can grow tubes in this way, and these are SEMs of materials I made. And you can see over here the diameter of the tubes. There we are. And they're all on the nanoscale. But one thing you also see is you see those areas highlighted with the orange circles. What those are iron clusters. Okay? For want of a better term, they are iron nanoparticles that have clustered together and formed these blobs. And you'll notice there are no nanotubes growing off of them. So if you do a residual element analysis, if you have an X-ray unit hooked up to your SEM, you can start taking elemental measurements, and you find out that the molar ratios are that roughly 40 to 1 carbon to iron, which is kind of terrible. Because if you actually take a look at the, amount of nanotube that's formed, a nanotube has probably about 1 billion carbon atoms in it per millimeter of length, and that iron atom has maybe, or that iron particle probably has a few thousand. So from a molar ratio, this is just telling me this reaction is terribly inefficient. It's horrible. But that doesn't stop people from using it, and just, it's still horrible. And why is it horrible? The answer is because aerosols, the way that they make these iron nanoparticles in aerosol form is you take a iron which is in something approximating a zero valent state, something like ferrocene or iron carbonyl. You throw it in there, it will atomize, it will then, those particles will combine, they lose heat by loss of surface energy, they will combine again and form bigger and bigger particles. And each one of these just gets bigger, and those are the types of things you see in there. And the reason for that is you can also see something like this, which is if you just do a simulation, if I have a bunch of iron atoms in a box, and I wait long enough, I start seeing that the particles end up forming these large blobs, and there's a cutoff. Well, why is that? And the answer is melting point. I told you there'd be some math. Okay, this is the Gibbs-Thomson relation. It shows the melting point of the bulk to the melting point of a particle that's small, and you can see right there that the smaller you get, the melting point drops. It makes more sense, since surface to volume ratios being what they are, it's going to melt at a lower temperature. And so what happens is those particles get big, they will cool off and become unreactive. There's no way you're heating their surfaces up again. The smaller particles will remain active for a certain period of time. But after a while, those small particles will, you run out of them. And you end up with a distribution in an aerosol in which only a small portion of the particles are in the right distribution size. So, if we use a revised growth process, the catalyst, and I hate to say it's a catalyst, and I'm in front of a bunch of people who have that catalyst expertise, all of that says to me what's more like going on, and why we can't control the beast until we name the beast. This is how I see it. It's not catalysis to me. This is more like a solute crashing out a solution. And if you were ever like me and were a high school chemistry nerd who did a sodium acetate supersaturated solution, it's the same thing putting on airs on the nanoscale. Here's something else that's particularly troublesome. I mentioned the number of nanotubes, and I'll explain why there's two crossed swords there in a minute. If you take that single wall tube and you count the number of atoms in it, you typically have about those many carbon atoms per unit length. A millimeter tube will form within seconds under conventional reaction conditions. And so there's only one problem, and that is that if you calculate, you get your copy of Castellan or Atkins out and you calculate the collisional rate, you find you're off by about 2 orders or 3 orders of magnitude. So it's not growing or extruding as fast as they think. They do under certain conditions. I once met Sir Harry Kroto, and he showed me, he drew me a nice little chart, which I didn't bring with me, I should have, where he was showing nanotubes growing inside of a controlled SEM environment. And there the reaction was taking place much slower, and you could actually see the cap extruding off. But as my high school math teacher, Mr. Walls, used to draw, when you have something that doesn't match, there's a conflict involved. And so I'm going to throw this out. This is not me doing anything except asking for feedback or asking you to please consider this. Polyaromatic hydrocarbons are rife in any carbon decomposition process. These are all found not necessarily on Earth, but out in outer space. As a matter of fact, the first found buckyballs was out in molecular clouds, and these species were flying around. Well, it turns out that those are present on nanotubes when they come out of the synthetic reactor. I know because I've done soxylate extractions and I've done supercritical fluid extractions, and we've run them through GCs and UV vises and stuff like that there, and we've confirmed that they're there. Okay, well, why should we care? Well, this is why. Sorry, there is a little quantum mechanics, but if it helps, I did these on my phone. There's a web app, or a phone app called WebMO, which allows you to calculate molecular orbitals. It's great to live in the 21st century, it really is. And the reason I show this is these are the HOMOs and LUMOs, and for those of you who remember your Woodman-Hoffman rules about the HOMOs and LUMOs having to react with things, you find out something interesting about this, and that is that when they start landing on graphitic surfaces, that HOMO-LUMO gap changes, and all of a sudden they start becoming quite reactive. And the result is that when these clusters end up absorbing onto the surface and the material is heated, they undergo some graphitization reactions. I've done studies where I've taken things which have been soaked in pyrene and then heated them up, and the pyrene is gone and carbon is there. So the question is, if growth is too fast by simple kinetic theory and there are these other species present, C and T cross-section gets bigger all the time. Right? And he's growing. It's not some little nanometer-sized particle. It's something that's approaching millimeters long. Okay, it has a really bad aspect ratio, but so the PAHs contribute. I don't know. Is this process epitaxial or catalytic? I don't know. I don't think anyone does. But it's important to ask the questions about this, because if you don't ask the questions and you don't frame it the right way, you can't talk about things like turnover frequencies in these types of environments. Okay? You can't use the tools of catalysis to describe something. You can't use the model of catalysis to describe something. And if you can't describe it, you can't control it. And so I'm going to leave it right there. I don't know how much time I've used up. I'm good? Okay, but thank you very much for putting up with my musings. And like I said, if you have any questions, come up to me, email me. If you have any disagreements, please. If I've missed something, I used to have a very wonderful physicist who worked with me. And every once in a while, I would propose something and he would say, Mark, I don't think it works that way. I could accept it. Thank you.
Other questions? I'll ask one real quick. I'm not in the carbon nanotube field, but can you use like that, your understanding of growth to control what tube you get, like the polygons and
Yes, you can. As a matter of fact, the key thing is learning how to make the nanoparticle catalysts, for one of a better term. I'm sorry, I'm using the same, I'm condemning others for using things that I'm using. There is a company I'm working with right now that is making iron nanoparticles that are 2.5 nanometers in diameter, controllably. And I'm dying to start sticking these into the reactor. I'm working with the Air Force Research Lab, nice guy named Engineering on hoping to send this up there. But to your point, I'm hoping, okay, I don't have any proof yet, but making the nanoparticles by a method, they use a method other than microemulsions. This is why I hate sodium borohydrate, because you can't control the particle size. These people have, so.
Then I have another question that's more on the application part, and that would you say that most carbon nanotubes have the transition metal contamination?
Yes.
Mostly iron?
Yeah.
Okay.
Yeah, unless they're willing to throw it in hydrogen fluoride, and I don't think anyone wants nanotubes that have been soaked in hydrogen fluoride. They're all banged up and damaged and awful.
Okay. Thank you. That explains a lot.
Thank
Okay.
you.
All right. Thank you so much again. It was really enlightening.